But I'm drawing a normal distribution. We know a normal distribution is a bell-shaped curve. It represents a distribution of a normally distributed population. It's symmetrical around the mean and the median, which are the same. And the properties that we're most interested in the population is the mean of the population, mu, and the standard deviation of the population, sigma. We learned in previous classes that because this is a normally distributed population, that there are certain things about the way that this distribution works that allow us to make certain, do certain calculations with our understanding of normal distributions. We know, for instance, that 50% of the population is to the left of the mean, and 50% of the population is to the right of the mean, right? More or less than, right? We know that if you're one standard deviation below the mean or one standard deviation above the mean, that represents 68% of that distribution. If you're two standard deviations above and below, that represents 95%, roughly, not exactly, but roughly 95% of the population. And if you're three standard deviations above and below, that represents almost everybody, 99.7% of the people in the distribution. Okay, so based on that, we can make certain predictions about, well, if a person is one standard deviation above the mean, what percentage of the population is even greater than they are? So we can figure out, well, this is 68%, so that means this is 32. So that leaves 16 on this half of the mean, because 50% on that half. So if 16%, 32% is accounted for, 32 and 32, 68% is accounted for, then 16% is left over here. And that's the proportion of that population that resides in that area, has that value or higher. And you could do it lower, you could do it in between. We did a lot of permutations of that. And in fact, we can go back at some point in the future and we can practice that a little bit more. We're going to bump into it a lot in the future anyway. The problem is that the thing that we're always interested in is finding the mean. The mean is elusive. We're never going to know. In almost 99% of cases, we're never going to find out what the mean is. The only way to know what the mean of the population is to sample the entire and measure the entire population, which is rarely practical, right? So even though that's our objective, we're never going to know what it is. So we have to substitute some other mechanism for determining what we think the mean is, or to get a good estimate of what the mean is. And the way we do that is we sample. Okay, and in the videos for this week, you saw there was a video about sampling strategies and so on and so forth. But for the most part, usually you're just doing a random sample. In fact, most of the problems that we're going to deal with are going to deal with random samples. To deal with samples is that when we take a sample, we learn something about the population. If it's a small sample, like for instance, if this room were filled right now, I'd have 30 people in it. Call that the population. If I were to take a sample of one, grab that one person and say, okay, what do you weigh? Well, I might get the heaviest person in the room. I might get the skinniest person in the room, or I might get the mean, the average person in the room. But it's just as likely I'll get the heaviest or the lightest as getting the person that's actually the mean, right? Because I'm only taking a sample of one. The problem with that is that when you only take a small sample, it makes it hard to make a lot of generalizations about what the mean really is. So we might take a bigger sample. Take a sample of size 10. Well, if I take a sample randomly, 10 people, and I average the weights of the 10 people, well, that average, just by reasoning this out, you'd assume that was a better guess at what the mean is than taking a single person, right? An even better thing for us to do, we take 25 people or 100 people or 1,000 people. The bigger the sample is, the more precise is our guess at the mean. More accurate, likely, is our guess at the mean. But there's no way for us to check how accurate it is. Because we're never going to know what the mean is. But what we can do is, because we understand normal distributions, we can take a look at what happens when you take repeated samples from a population of a certain size. The sample size is repeated over and over again, and you take that sample. Let me move that over and get another page here. Okay, so on the left here, I'm going to put the sample distribution. The population distribution. Okay, here's mu, and here's sigma. Okay, now, yes, you can't see it there. It's not dark enough. Yeah, that's weird, right? Oh, I wonder why that's happening. Let me take a quick look here. Did it show up yet? No? Oh, there it goes. Okay. You know, I should have. Okay. Oh, you know what happened? I paused the screen. I wonder if people online yes, still can't see the screen. Yeah, there were complaints online. I just didn't pay attention to them. They were right. Okay. Okay. Now you should be able to hear me again. Okay. I don't know why this is fighting me today. Okay. So let's say I take repeated samples of size 10 from this population. Say it was blood pressure. Which one's the lower one? Diastolic is diastolic is the lower number, right? Yes. Am I right about that? Okay. So let's say that the average is for a population is 80. And let's say the standard deviation for the population, now we normally don't know this, standard deviation for the population is 5. Okay. Well, I say to myself, okay, now if I randomly select one person from this population, there's a 50-50 chance of him being over 80 or under 80. There's also a chance of him being exactly 80, but that's not too likely, right? So it's 50% of the people are over 80, 50% are below 80. Okay, now if I randomly select someone again, well, you know, the range of numbers here, remember I said that practically everybody is within 3 standard deviations above or below the mean. So we might have people as low as 65. Thank you. Excuse me. Low as 65, low as 65, or as high as 95 in this population. But if I randomly select 10 people, I wouldn't expect that wide a range anymore from each group of 10 people, because I wouldn't expect to get 10 people that are 60, whose blood pressure is 65 if I'm randomly selecting them. I would expect to get some lower, some higher, some in the middle. So my average is going to be closer to the true mean than any individual sample, any individual person I might sample, likely at any rate. Okay, so now if I take a sample of size 10, well, sample of size 10, what's going to happen now is that if I take that sample over and over and over again, 10 people, take the average, 10 people, take the average, and I take all of those averages, and I find the average of those values, what do you think the average of all of those samples is going to be? Anybody want to hazard a guess as to what those sample averages is going to be? About 80 also, right? Half the time the average will be less than, half the time the average will be more than the population. But what do you think is going to happen to the range of numbers here? It's not going to be as wide, right? It's going to be narrower. Well, if you look at, I'm not going to go into all the stuff we went into in the videos and stuff like that for this week's class. But if you look at those, the relationship between the sample size and the standard deviation of the population is that the standard deviation of these repeated samples, when we set them up in a new distribution, is equal to the standard deviation of the population over the square root of the sample size. I'm gonna cheat here. I'm gonna call that 16 instead of 5, instead of 10. Make it easier on myself. Okay, so the standard deviation for all of these repeated samples, if I took a sample of size 16, is going to be 5 divided by the square root of n, which is 16. Square root of 16 is 4. 5 over 4 is going to be equal to 1.25, right? 1.25. Okay. So now let me think about this. 3 standard deviations below and 3 standard deviations above is going to capture almost all of the results. So what's that going to be? Well, now that's going to be, let's see, it's going to be 3.75, about 4. I'm going to call it about 4, less than 80. So it's going to be maybe at the lowest 76 and at the highest 84. Wow. Now I have a much narrower distribution based on all those repeated samples. Well, how about if I take a sample of size 100? What's going to happen there? Well, if I take a sample of size 100, I apologize for the scratches here, but I don't have my graphics tablet with me today, unfortunately. So if I do that, then the standard deviation of the repeated samples of that size 10, size 100, is going to be equal to sigma over the square root of n, which is again 5 from the population, over the square root of n, which is 10. So it's going to be equal to 1/2. But again, the middle of that distribution is going to be 80, right? Of all those repeated samples. Half the time be above 80, half the time above. Yes? Sample distribution approximates the mean of the population. So let's take a look at what happens here. Well, now the standard deviation is 0.5. So 3 standard deviations below is going to be 78.5. And 3 standard deviations above is going to be 83.5. It was 0.5, 81.5. I'm sorry. This is going to be 78.5. And this is going to be 81.5, right? Which is over here and over here. What happens to this? Now our sample distribution is much narrower. It's still around 80, but it's much narrower. Well, why is this of any value to us? Well, we're never going to take 1,000 samples over and over again and create one of these distributions. But we're going to take what we understand about it and use that instead. And by the way, when I talk about what the standard deviation of the sample distribution is, I usually don't use the term standard deviation or sigma. What do I usually use instead? Standard error. That's the standard error. So if you don't hear standard error, you know you're talking about the sampling distribution. Okay. So now, quick application of this. Okay, so I'm going to really do a really fast application of this. Okay, and this is going to be my sampling distribution. No, maybe I'll make this is my population. Okay, here's mu. I don't know what mu is. Sigma, I'm going to say for our purposes that we know that sigma is equal to 20. Okay, and in this case, we're talking about the average amount that you spend on books in a semester. So CUNY, School of Public Health students spend on books. I'm going to say that the average amount is $400 per semester, right? That's the mean. We'll never know the mean unless we go around and ask everybody what they spent, but we're going to start with the assumption that we know these two things. So now, if I say to myself, I want to find out what the average that School of Public Health students are spending on books, but I don't want to have to contact every public health student. Instead, I'm just going to sample 25 students. So I'm going to take a sample of size 25. Okay, so now I'm going to say to myself, okay, I'm going to take a sample of size 25, and I'm going to say to myself, okay, let's find out what that average for that sample is. And let's say I get the average for that sample is equal to, say, 390. Okay, is it the same as 400? I'd have to be awfully lucky to get exactly 400, the same as the real population mean. That'd have to be really lucky, right? But 390 is not such a bad estimate either, right? So now based on what we understand about samples, I know what I know what the mean for my 25 people were. But now, what can I see? I know that a sample of size 25 gives me a certain amount of latitude about understanding how close I'm likely to be to the real population mean. But now, how can I quantify that? Okay, so let's take a look at how we might want to quantify that. Well, first thing I'm going to do is I'm going to draw another distribution, which is going to be our imaginary sampling distribution if we had done this over and over again. Okay, and for the moment, I'm going to say for this class and the next class, most likely, I'm going to say maybe not next class. We'll see. I'm going to say for this class that we know the population standard deviation. Not impossible. Sometimes you're doing a study with where you're sampling a small group, but it's based on that group being some other group similar to it having been surveyed large numbers before. So you think you have a pretty good handle on the standard deviation. I'm going to assume I know sigma, but I don't know mu. Okay, so let's think about this. If that tells me that I know what I can calculate the standard error for a distribution of repeated samples of size 25. So the standard error is going to be 20 sigma over the square root of the sample size, which is 5. So the standard error is equal to 4. Well, how does that help me? Yes. I'm sorry, say again. Yeah, square root of 25. Yeah. Okay, 25 square, it's the sigma over the square root of the sample size. I'm right over here. Sigma over the square root of n, right? In other words, 20 over the square root of 25. Yes, I heard a question.
Is this similar to the last question?
Yeah, we're going to get to that, except they're proportions. We're going to get to proportions later. I mean, I'm sorry that question's in there because that question is a little bit trickier than just a simple numerical variable because it's a proportion, but we're going to get to that. I haven't forgot about that. A lot of people have asked me about that. Okay, so you do have the tools to do it. I think the last folder is sample distributions of proportions, but we'll get to that shortly. Okay, so at any rate, so I know that my mean was 390. And I know that if I take repeated samples, I expect that my standard error for those repeated samples is 4. The spread is based on a standard error, standard deviation of 4. Well, let's for the moment pretend that that is our starting point for our guess for our population mean. It's not our population mean, it's our sample mean. So let's start with that point. So now if I take that 390, okay, if I were to assume that that were my real population mean, if I took repeated samples, I would expect 95% of the samples that I take to be between what and what? 390, right? Less 8, right? Which would be 382. And plus 8, which would be 398, right? I'd expect most of them to be, 95% of them be between those two numbers. Yes. You're not going to really do this. I'm just kind of two standard. Remember, it's two standard errors, not one standard error. To the left and to the right is 95% of the possible outcomes. Okay, so now I might yes.
The standard error formula is
Sigma
over and
the square root of n.
Square root of
yes.
N.
So
and is something. For this that one that you just calculated in that form.
Well, sigma is 20, right?
Or from way okay.
Yeah. Sigma. I'm saying that we know the population standard deviation, right? Which is just something we're going to do for this week's exercise. And sample size 25, so square root is 5, so it's 20 over 5 or 4. So we would expect that 95% of the results for these samples, if we took them over and over again, to be between 382 and 398. Okay, I'm gonna erase this 400 because we don't know what it is. I have to erase it because I just realized that's not going to work. Okay, so at any rate, now we're not going to really do this. However, what we're going to do is we're going to take a twist on this, and we're going to say to ourselves, if 95% of the time I would expect, if this is the right amount, I would expect to get this, I can kind of say instead, maybe I can say instead that we're 95% certain that the real population mean is between these two values, 2 standard errors above and 2 standard errors below. And let's give that range a name. We're going to give that range the name the 95% confidence interval. Okay? So how did we get that 95% confidence interval? Okay, I took X bar, our sample mean, plus or minus our the z-score. The number of standard deviations is the z-score times the standard error, the number of standard errors. Okay, so what was that? That was 390 plus or minus the z-score, which is 2, right, for a 95%. That's the empirical rule. Times our standard error, which is 4. So I would take 2 times 4 is 8 and add and subtract that from 398 to get a range of 382 to 398. Okay, and I'm going to call that my 95% confidence interval. Okay, yes? Is the z-score for the number of standard deviations, or in this case we call it standard errors because it's the samples. Yeah, standard error is the same thing as standard deviation, except it's specifically for a sample distribution. Where did I get the? I'm sorry. The 4? Oh, 2 times. Right. It's the z-score is 2. 95% is two standard deviations below the mean and 2 standard deviations above. So that z-score is 2. In other words, it's 390, right? 390 plus or minus 2 times 4, or 8. Right, 95%. In other words, 95%, the middle 95% of all the possible outcomes. Right. Okay, except that I just lied to you. Is it really 2? Yeah, it's 1.96. That empirical. The empirical rule that we started with is only an estimate. Okay, and I'll show you where we get it from.
But what about the table?
Okay, we're going to do that right now. Okay, let's get the table out. Okay, so here's the table. Now, if I have 95% of the distribution in the middle, how much does that leave in the tail, at the bottom, and the top? 2.5% at the bottom, 2.5% at the top. So we need to, and since this table gives us the tail to the left, I'm just going to look up to see what z-score gives us 2.5% in the bottom part. So the areas are all the numbers in the middle. So I'm going to find the area that represents 2.5%. Okay, so let's see, 2.50. Here's 2.50 right there, right? So what z-score gives us 2.50 or 2.5%? 1.96. Okay? Okay, how about 99%? How much is left on the left and the right if you want the middle 99%? 0.5, right? So let's say 0.005. 0.005. We're not going to get the exact number, I think. Okay, let's try this. We'll use that one. Okay, what is that? That's 2.58. Oh, let's remember that number, because I might ask you not what the 95% confidence interval is, but what the 99% confidence interval is. So we might need that number 2.58 later. How about a 90% confidence interval? The middle 90% of the distribution, only 5% on this side, 5% on this side. I'm not even going to bother to look it up. I know it's 1.64. Okay, so we're going to use those 3 numbers. When we're looking for a 95% confidence interval, we're going to use 1.96. When we're going to use a 90% confidence interval, we're going to use 1.64. And we're going to use a 90% confidence interval, we're going to use 2.58. Okay, yes?
90% in the lecture, it was 2.56. So
Not 99.
we use
99.
99,
Yeah.
2.56. So
2.58.
So we should not use 2.
No, you use 2.5. Did I say 2.56 in election?
Yeah.
It's because I'm old and I forget. It's 2.58.
What's for 90? It's 2.1.
8.
For 99%,
Right. For 99%. 1.96 for 95%. And 1.64. And you don't have to believe me. If you ever forget it, you can just go to the table and look up what the number has to be. Just the same way we deduced it now. Okay, so now let's say, here we go. So let's say what I just predicted, based on our sample, I predicted that the true population mean is between 382 and 398. Now, I don't know what the real mean is, but what I do know is that when we calculated it, when we took a sample of 25, we found the average to be 390, but we know that's not going to be the exact mean. So I'm going to say, well, our finding is that the mean for our sample was 390, and we're 95% certain that the true population mean is between 382 and 398. Now, if I wanted to be 99% certain of capturing the mean, right? That means 5% of the time. If I do this 20 times, 5% of the time, I'm going to miss the mean. It's not going to be in between there. I'm going to be wrong, right? What if I want to be 99% certain? What changes here? The z-score. Instead of 1.96, we use 2.58. So if we multiply 2.58 times 4, it's a bigger number. And we're going to subtract and add that to 390. So what happens to our confidence interval? Does it get wider or narrower? It gets wider because we're adding and subtracting a bigger number, right? 2.58 times the standard error. Standard error stays the same. But so now it's wider, which makes sense, doesn't it? It makes sense that if I have a wider range, I'm more likely to capture the mean. But now if I was willing to sacrifice, my accuracy, and I was willing to say, I only need to be 90% sure. Well, then I can use 1.64. So now it becomes a smaller number you add and subtract. 1.64 times 4, the standard error. And that's a smaller number that you add and subtract. Okay, so that's it. That's all there is to this. That's it. This doesn't really get much more complicated than that. Now, what I'm going to do is, because I know we had an issue with that particular problem, I'm going to jump over to proportions. Okay, good. All right. It's the same deal. Okay. Let's say I go out and I survey 1,000 people. N equals 1,000. And usually with proportions, usually dealing with fairly large samples. In fact, there is a minimum sample size that you really need to be working with. Now, that large sample, right, as it happens, out of that 1,000 people, right, I find that, let's see, let me guess. I'm going to say that, what can I do? Let's say that out of that 1,000 people, 200 have had a flu shot this year. Okay? So, what's the population proportion of people that have had flu shots? Not my sample. What's the population proportion that's had flu shots? Trick question. Do we know what it is? Oh, what percentage of New Yorkers had flu shots this year? We don't know it. We're never going to know that, right? We're never going to know that, because to know that, you would have to go to every person in New York and ask them if they had a flu shot, and they would have to not lie to you, right? So we're never going to know that. However, what I do know is I randomly sampled 1,000 people. 200 of them told me I had a flu shot. So I'm going to say our sample proportion is equal to 20%, 0.20. That's our sample proportion. I'm gonna remember, like with X, we made sure that we distinguished it from the population mean by calling it X, but also putting a bar across the top. I'm going to put a cap on that. That indicates to me that that's the sample proportion, the 20% from 200 out of 1,000. Okay. So now, if I go back and sample another 1,000 people, I might get 0.21. I might get 210 out of 1,000, or 199 out of 1,000, and so on and so on. So the proportions have their own sampling distribution. Works exactly the same way. So in order for me to, now, right now, it looks like, I think, based on this nice big sample, that 20% of New Yorkers have already had a flu shot this year, right? But I need to know how well do I really understand it? How well do I know that? I'm never going to know the real population distribution. So I would like to know what level of confidence I can have in that number, what range I can define as my confidence interval. Well, now, in order to do that, we need to calculate the standard error, right? Just like before. When we're dealing with a proportion, the standard error is calculated by taking the square root of the proportion times 1 minus the proportion, 1 minus the proportion, over, I really missed my tablet, over the sample size. All of that's underneath that square root. Okay, so notice that I put P, like the population proportion, in here. By all rights, we should really use P if we know it, but we don't, so we really just use P cap, right, instead of P, because that's all we know. That's the only tool we have is P cap, right? So what is the standard error equal to for this problem? The standard error for this problem is equal to 0.2 times 0.8, okay, over 1,000. Okay, and what's that equal to? It's equal to the square root of, let me get my calculator out, and I'm going to check online in a second, see if there are questions. All clear, let's clear that. Okay, so it's 0.2 times 0.8, that's equal to 0.16 divided by 1,000 is equal to this, and I'm going to take the square root of that. And it comes out to be 0.01. From our purposes, normally I would say don't round too much, but for our purposes, so we can get out of here tonight, I'm going to call that 0.013. Okay, it'd be nice if you carried another decimal place, just so you have a little bit more room to round it later. 0.013. Okay, so the standard error is equal to 0.013. So now I have to calculate my confidence interval for that proportion. What's it going to be equal to? Same as before. Now, what do we call a sample mean or a population? We call it a point estimate. The sample mean and the population proportion are both point estimates, the number that we think is the mean. So I'm going to take our point estimate for the proportion P cap, and I'm going to add and subtract. Now I have to decide what z-score to use. For a 95% confidence interval, what should I use? 1.96. We're done with 2. We've graduated from 2. We're 1.96 from now on. Times 0.013. I'm sorry, 0.013. Yes. Oh, we're gonna get it. Yeah, you might be getting ahead of me a little bit. The idea there is that, remember I told you that we know the population standard deviation, right? That's usually not true. The reason why I'm assuming that we can work with these numbers as if they're the population standard deviation is because right now I only want to introduce one element of uncertainty, what the mean is. Later on, we're going to find out, well, gee, what if I don't know the population standard deviation? What am I going to use then? Then you're forced to use the standard deviation of the sample you took. And when you do that, you have to use a special table called the t-table. But you're a t-table. Okay, when you don't know the population standard deviation, you have to find some way of estimating what it is. So just like you use the sample to find the mean, an estimate of the mean, use the sample standard deviation to use it as an estimate of the population standard deviation also. Problem is now you have 2 levels of uncertainty. You got the mean and the standard deviation are uncertain, so you have to use a special table which makes up for that uncertainty called the t-table. We're not getting into that next week. Get into that next week and the week after, so don't worry about that right now. Yes? Exactly right. Exactly right. But for this week, we're just worried about, I'm going to tell you, you know it. Okay.
So in this case, the proportion will be representing the mean.
Yeah, the standard error would be calculated that way. What happened to that? Oops.
What is the reason for that?
I'm sorry, what's the reason for it?
Using the X in order to calculate the.
Because we don't know what the real population is. What the real proportion of the population is. So we use it. We're doing this just like we would do it for a mean. We're using it for a proportion also, because it's the same deal. It's going to be normally distributed. In other words, if there's 20% of the population took the flu shot, it's going to be, if you randomly sample people, it's going to be it's going to be normally distributed.
Oh, okay,
All
so
of your
proportion.
results. Yeah. Okay. So what is that going to be equal to? Trying to find my calculator. Disappeared on me. Let me quit it and start it again. Okay, so it's going to be equal to 1.96 times 0.013 is equal to 0.025 roughly. I'm going to, 1.96 times 0.013 is equal to 0.025 roughly. I'm going to clear out my memory here and I'm going to put this in there. Clear. And I'm gonna let's see. I'm gonna add and subtract that from my p cap. What was my p cap? It was 0.20, right? Minus 0.025 is 0.175. Okay, I'm gonna write that down. Maybe no, I'm not gonna write. You guys write it down for me. I don't want to lose my calculator again. I'm gonna clear that, and now I'm gonna do the same thing. I'm gonna say 0.20 plus that standard error, that the standard error times the 1.96, and that's going to be 0.225. So what was it again? 0.17 what? 175, and the second number was I'm sorry, 225, roughly. Okay. So what can we say now? Our point estimate for the proportion is 0.20. But we're 95% sure that the true population proportion of people that have had flu shots this year in New York City is between 17.5% and 22.5%. So see how we can use our understanding of how sample distributions work to help us understand how close, what kind of precision or accuracy that we have predicted the mean. Does this mean that the true proportion is between those two numbers? No, we're only 95% certain. It could be 5% chance we're wrong, that it's lower or higher than this. If we want to be more certain, we would take p cap and we would add and subtract 2.58 times 0.013. And that added and subtracted to our 0.20, that would give us a 99% confidence interval. In other words, it's a wider interval, so we can say we're 99% certain that the real proportion is between those two numbers. Okay, we could do 99.9 if we wanted to. We could do 99.999. We're never going to get to the point that we're going to know for sure that the population proportion is going to be between those two numbers unless we go out and sample everybody. Right? I mean, that's always going to elude us. But that's why in these kinds of studies, we're forced to learn statistics, not like physics, right? Physics, I hold the ball up here, I let it go. We know exactly how much time it's going to take to hit the ground, right? Because gravity works one way, right? We know it's never going to go up, right? In statistics, we're dealing with probabilities. We can't sample the whole population, so we're stuck having to do something else. Let me go on. Let me see how the guys online are doing here. Okay, how are you guys doing online? This makes sense to everybody. It's basically, is it starting to sink in? Okay. That's really as hard as this gets. Yes. Yes. What part are we stuck on? Okay, I'll do that again. Let me get a fresh piece of paper. Okay, so now I went out, did a survey. I sampled 1,000 people. That's our N. That's the sample size, right? Out of those 1,000 people, 200 of them, I'm going to change the number. 300 of them had a flu shot this year. Okay, so what proportion, PCAP, I'm going to call it, what proportion of our sample had a flu shot this year? Yeah, 30%, 0.30. Okay, so now I need to calculate. So now I know that this particular sample came out 30%. It could have come out 29%, 290 people, so on and so forth. I don't know what the real population proportion is. I only know the 1,000 people that I sampled. So now I want to calculate a confidence interval for this result. So that confidence interval, the way I calculate it is I'm going to calculate P-cap, right, from our sample, plus or minus some z-score. And that z-score is going to depend on whether I want to be 90% certain, 99, 95, or 99% certain that I captured the true mean, times the standard error. Okay. So P-cap we know is 30% in this problem. The z-score is going to be either 1.64, 1.96, or 2.58 for 90% confidence interval, 95% confidence interval, or 99% confidence. So now we have to calculate the standard error. So standard error before we calculated is the standard deviation of the population over the square root of n. For a proportion, we have to calculate it using this formula. The square root of p, or p cap, for our case, times 1 minus p over the sample size. I wish I could draw this a little bit better. Okay, so let's do this calculation again. So that's equal to the square root of, in this case, p is 0.3 times 0.7, yep, over 1,000. Okay, so let's get the calculator up again. Okay, I'm going to clear this out. So 0.3 times 0.7 equals this, divided by 1,000, equals this, but we're not done. I've taken the square root of the whole thing, right? We just calculated what was in here. I take the square root of it, and it's equal to 0.0145. 1.45%, right? That's where our 1.03, our 0.013 came from before, except now I'm using different numbers, so it came up 0.0145. Okay? Are we okay with that so far? Okay. I mean, in the beginning, I'd like you guys to understand this. In the beginning, if you got to go on autopilot to do this, that's okay for now, right? And as you do these problems, you'll get a feel for them, and it'll make more sense to you. A light will go off. I promise. At some point, a light will go off, and it'll make more sense. But if you have to do it on autopilot, just use the formula and do this. Then that's okay for now. That's okay for the first week of this. Right? So now, what do I do now? Well, this is, let's see, this is 0.0145, I'm going to call it. I'm going to clear this out, 0.0145. So what is our 95% confidence interval? It's 0.3 plus or minus 1.96 times our standard error, which was 0.0145. Right? That number seemed kind of weird at first, right? Because it's such a small number, but it's really almost 1.5%. And we're going to wind up doubling it to 3% and adding and subtracting it to the 0.30, to the 30%. So that's where we get our range there. Okay, so I'm going to go ahead and do this, 0.3 plus or minus, and I'm going to my calculator again. Clear. Okay, I'm going to call it 0.0145 times 1.96 is equal to 0.028. 0.00, I'm just going to use the first part of that, 0.028. Like I said, if I could get you guys not to round until you're all done, I would prefer that. But I need to get done here at some point with these problems. 0.028. So that is the the product of multiplying 1.96 times 1.45%, 0.028, 0.028. So now I'm going to add and subtract that range from 3. So that's 0.3. That's going to be equal to 0.272, comma, 0.328. Right? 27.2% to 32.8%. Okay? Yes, otherwise, yeah, and that's why you take a sample, right? That's why you're going to have a sample mean because you took the sample. You're going to have the sample proportion because you sampled 1,000 people or 100 people, or so on and so forth. Okay, so there is that. Is there a particular problem on the homework? Oh, well, let's take that look at that problem on the homework right now, right? Yes. Yeah, I'm listening. Okay. Now, I think, unless I screwed up the problem or I didn't realize what the issue was when you guys talked about it, I think it's going to be easy as could be right now, or it should be. Otherwise, there's something wrong with the problem, which is possible. Okay, let's see. Where are we? Let's go in here. Okay, and let's take a look at that homework. Okay, and that's number 4. Okay, and I'm going to believe I'm taking that homework. Okay, I'm going to go down here. And we were down here. I'm going to start with 11 and 12 is what everybody was asking about. I'm going to start with 10 though. The probability an infant is born prematurely in Mexico is 0.15. I don't know how true that statistic is, but that says that 15% of children in Mexico are born prematurely. What is the standard error for the proportion of premature births for repeated samples of this population of size 25? Okay, so the standard error is going to be equal to, that's from a sample, I would presume. So the standard error is going to be equal to the square root of p times 1 minus p over n. Okay, so let's get our calculator out. Yeah, you have to use 10. Yeah. Okay, the other problems are just asking what the, oh my goodness. Okay, wait a second. There is a problem here. We changed it to sample size of 625. Yeah, I know. I'm just looking ahead to the other ones. The sample size changed. Yeah, on that one we just asked you what the standard error was. Okay, and the standard error is equal to 0.15, right, times 0.85 divided by the sample size is how big? 25. That's equal to this, and I got to find the square root of that. Okay, so the standard error is 0.071. Okay? That's all it asks for, so we stop there. Okay. 0.15 times 0.85 divided by 25 and take the square root of the whole thing. Okay. All right, so let's take a look at number 11. We would expect 95% of samples of size 625 to be in between. Now let's assume it's the same population, 15%. Our P is 15%. Okay, except this time it's a sample size of 625. And they're asking us for the confidence interval. Yeah, it's a badly worded question. I agree with you guys. They're asking us for the confidence interval if you had taken a sample of size 625. So, and you want the lower level, the lower limit of the confidence interval and the higher limit. Okay, so let's go back here. And this time, okay, I'm going to do the same thing. I'm going to calculate my confidence interval. Okay, let's see. It's going to be 0.15, our standard error. 0.15 times 0.85 divided by, what's the sample size this time? 625 is equal to, oops, I did something wrong there. Hang on a second. 0.15 times 0.85 equals this divided by 625. Our standard error for that sample size, different sample size, is going to be the square root of this number, is going to be 0.014, right? 1.4%, 0.014. I'm going to put that into memory plus. So now, in order to calculate what the confidence interval is, right? Let me, you guys remember that, no, let's see. That's the standard error. I'm going to multiply that by 1.96. 1.96 times the standard error is going to give me, what do we call that number we add, subtract from the p-cap or from the mean? Remember what we call that? Well, what if I said, I think your weight is 150 pounds, plus or minus 10 pounds. Well, we might call that the margin of error, right? So we call that the margin of error. When we multiply that out, we call it the amount that we add and subtract, we call it the margin of error. So I'm going to multiply this by 1.96. And it's equal to 0.028. Okay, so I'm going to clear that out. 0.028. I'm just going to put 0.028 to simplify things a little bit. I'm going to put that in memory. Okay, so now I need to add and subtract that from my proportion, which was 0.15. My predicted proportion, which was 0.15. 0.15, 15%, right? That's what we had in the number 10. 0.15 minus 2.8%. So the lower end of our confidence interval is 0.122. The p-cap is 0.15. Remember, we're talking about proportions now. Okay. 0.15. Yeah, it's not really that well worded, but to tell you the truth, that's the only proportion that's mentioned in those three problems. Okay, so that's if we add it to 0.15, it's going to be 12.2%, clear. And then if I subtract it from 0.15, add it to 0.15 minus 1.196 times the standard error. I messed this up. 0.15 minus 0.028. Oh, I just did that. Clear. 0.15 plus 0.028. I can't win. 0.15 plus 0.028 is equal to 17.8. So it's 14.4, I think it was, to 17.8 is the 95% confidence interval. Correct. And the lower number would be, I think it was 14.145 or something like that. Okay. It's the same operation, whether it's proportions or whether it's the means that you're dealing with. You need to take your sample, see your sample size, find your standard error, calculate your standard error, decide what level of confidence that you want. So you know what that z-score has to be that you're going to multiply by. And then add and subtract that margin of error that you calculate by multiplying your z-score times the standard error that you calculated. Okay. Now I think I posted two sample assignments, right? 2 extra printouts and stuff. Oh, is that the next week's already? Yeah. I didn't even realize it was posted yet. Oh yeah, I didn't mean to. I guess I did post it. Oh, now okay. Now week 7 gets a little bit more complicated, doesn't it? Huh? Well, I don't count the exam week, so I'm kind of yeah. Well, if you look at the date ranges, it'll make more sense to you. So yeah, I made them available a little bit early because, to tell you the truth, these 2 weeks are kind of similar, right? We're introducing this idea of confidence intervals and proportions and means and sample distribution. So they're kind of similar. So I don't think did I make the videos available too for next week? I did. Yeah, I think I just posted the homework and without but not the week's videos yet. They're there already. Oh, let me take a look. Let me see what I posted. Rather than guess at this, let me see what I did. I'm dealing with a couple of classes here, so sometimes I mix this stuff up. Hard to keep track. Weekly sessions. See what's available. Oh yeah, week 7's available. Week 8's not available. Yep. Okay. Yeah, I kind of got a little bit ahead of the game. No, that's not posted. That's not available. Yeah, see, it says not available. You can't see that. That's going to appear on the 24th. Okay. Okay, and that one is, and so this week you're starting to see stuff that involves, yeah. On for this week, right? For this week. That's good. That's a good point. You know what you're doing? You're getting ahead of my other class. Confidence interval for mean, confidence interval for proportion. Self-test. Let me see what self-test 2 is. A random sample of 250 bats, 75 are former students. What is the point estimate? Oh yeah, this is a Halloween special. Right? I don't know if you noticed that, but obviously. What's the point estimate p-cap for the proportion of bats? Well, out of 250, so 75 over 250, right, is the proportion, right? Okay. What is the margin of error for the true proportion of bats? What's the margin of error? It's 1.96 times the standard error. So if you know 75 over 250 is the proportion, what does that come out to be? That comes out to be maybe 0.25. Then you know that the standard error is 0.25 times 0.75 over the sample size, which was 250. Find the square root of it. Now you know the standard error. The margin of error is 1.96 times the standard error. Okay?
So for the first question, all you have to do is
Yeah, take the proportion. 75 over 250. Exactly. That's it. Right? So the second part, the margin of error, you just take this, you find it skips the standard error step, right? You have to calculate, you have to know you need the standard error to calculate the margin of error because it's 1.96 times standard error. Okay, and then what's the lower value for the 95% confidence interval? Well, it's the 0.2, whatever 75 over 250 is, which is it? No, it's 0.3. It's 0.3 minus the margin of error, and the next one is going to be 0.3 plus the margin of error, right? So that's going to be the next problem. So you really you have all the tools to do that problem. The only thing that threw you a little curve is that I didn't ask you for the standard error. You had to figure out for yourself, oh, in order to calculate the margin of error, I need to know the standard error because the margin of error is the total amount that I'm going to add and subtract from the proportion. Right? Here, let me clarify that. Okay, so for that, okay, p cap is equal to 75 over 250, right? Which is equal to 0.3. Okay, I'll take your word for it, right? So the standard error is equal to 0.3 times 0.7 over 250, right? Right, and take the square root of that whole thing. Right, what does that come out to be? Calculator. Clear everything out of here. 0.3 times 0.7 is equal to 0.21 divided by 250 is equal to 0.008. Square root of that is 0.029, let's say. Okay, so this is equal to 0.029, right, is the standard error. So now what's the margin of error? Well, let's see. If I'm going to find my confidence interval, it's going to be p cap. Whoops. P cap. I'm really sorry I left that thing up. P cap plus or minus 1.96 for a 95% confidence interval times my standard error, right? So what is that? That's going to be p cap, which is 0.30, plus or minus 1.96 times my standard error. My standard error is 0.029. 0.029. So I got to go back to my calculator. Okay, I'm gonna round this one. 0.029 times 1.96 is equal to 0.057. I'm going to call it 0.057, right? So this whole thing, plus or minus 0.057. And we're going to add and subtract that from 30 to get our confidence interval. And what do we call this? That's our margin of error. The amount that you're adding and subtracting. In other words, the z-score times the standard error. Right? Just gave it a name. Right? So something you've been doing all along, I just gave it a name. Okay? All right, let's call it a night. I have to get on to another class here. So you guys online, let me see. Homework question number 1. Homework question number 1. Which homework is that? Homework question number 1? Is that question number 1 on homework 4? Okay, I don't see a response. Okay, we'll pick this up again. All right, so we'll be back here next week. Put questions into the discussions group so I can address them when we get together during these sessions. Okay? Okay, good night, guys. Oh, assignment 4. Okay, I didn't get a look at question number 1. Let me see. Assignment, weekly sessions, homework assignments, page, assignment 4. Continue. Number 1. Among adults in the distribution of albumin is roughly symmetrical with mu. That's our mean. Mu equals standard deviation 9.25. Suppose you select repeated samples of size 20 from the population. Calculate the mean for each sample. What would you expect the mean of the samples to be? We'd expect the mean of the samples to approximate the mean of the population, which is 29.5. Okay. And what would you expect the standard deviation for the repeated samples to be? Well, we would expect it to be the standard deviation of the population divided by the square root of the sample size. Sample size was 20. Okay, so we would continue to go through that from that point. Let me take a look through this, see how other guys are doing it. Okay, so good night, guys.